So today we'll keep talking about ion chromatography, okay? So can you guys hear me? Is it okay for you? Can you hear me clearly? Thank you. Okay, so that's good. So we can start. Thank you. Okay, so for ion chromatography, we mentioned a little bit last week, right? Just a little bit last week. And then so for ion chromatography, we say that ion chromatography actually is an analytical technique. So let me see. So we're going to talk about this one. Hold on, sorry. Oops, two students. Okay. Okay. Still many students coming. Yeah. Okay, so we see that for ion chromatography, it's an analytical technique for the separation and determination of ionic solutes, right? Okay, so normally it's just in water, we say. So in general, especially for the environmental sample, like we say in wastewater sample, like in river sample and in rainwater and so on. So, and also in industrial process, like the metal industry and industrial wastewater in biological system, in pharmaceutical sample, in food sample and so on. So it actually has pretty wide application. So, and it's also a kind of liquid chromatography technique, right? Because it's a mobile phase, it has mobile phase, it has a stationary phase. And stationary phase normally is also, say, in the form of small diameter uniform particle packed. So it's packed column. And diameter of the particle is still like 5 to 10 micrometer, okay? So it's just packed into the column. And the column can be, is made of rigid material such as stainless steel or plastic. And it's generally very similar to HPLC, and the column length is about 5 to 30 centimeter long. And so an internal diameter is same, is about, say, 4 to 9 millimeters. So also require high pressure pump to pump it through. And then so flow rate is very typical, just 1 to 2 milliliter per minute, right? Okay, but we just mentioned that because like for the mobile phase now using pretty strong acid or base like that one, so it's can be corrosive, so that's why. So and for the tubing, so you want to use those like say can resisting this one, corrosive one can be the peak one. And also when later on when we talk about so anion chromatography, and this one, the mobile phase sometimes can even use very basic solution like sodium hydroxide. So for that one, so then those for the mobile phase reservoir for the bottle, you want to use plastic bottle. You want to use plastic bottle, not really so glass bottle, because it's so this sodium hydroxide can dissolve silica in the glass, right? So that's why you have to use plastic bottle. And also you need to degas, and then so better to prepare freshly the mobile phase, and also you want to flush the helium gas to go through, and to avoid the CO2 get in, because the CO2 get in sodium hydroxide, then you will form sodium carbonate, right? Okay, so and so that's why. So there's something like pay attention to, okay? And for the detector, so it'll be like say mainly used will be conductivity detector for ion chromatography, but later on we'll mention that. So if we're using conductivity detector, and then you have to think about whether you need to lower so the mobile phase background signal or not, okay? Because all the ions, they're conductive, right? Okay, so for the mobile phase, if you're using strong acid or strong base, so those ions, they're conductive too. And how we can remove the signal from the mobile phase, so how we can lower the background. So and then so that will be something we talk about when we talk about the detector part. Okay, so it's something like say a little bit different from the normal HPLC. Okay, and then so that's it. And I think we talk about this a little bit, right? We say like for ion chromatography, and we'll focus on the ion exchange chromatography. We'll quickly mention so ion exclusion chromatography. This one, ion exclusion and ion exchange chromatography, they have different mechanisms. And for ion exclusion chromatography, we use it to most of the times measure those weak organic acids. Okay, so for example, oxalic acid and succinic acid. So this is like C2, C3, C4, C5. So those carboxylic acid diacids we can use the ion exclusion chromatography. For ion pairing, that is one we actually already mentioned. We also say later on we're going to learn capillary electrophoresis, and this one can also used to separate ions. But the difference of capillary electrophoresis and ion exchange chromatography is like so ion exchange chromatography, this one. So this one. So you have to use like a different column for the ionine and cation. We have the ionine ion chromatography and cation chromatography. But for capillary electrophoresis, you can analyze the cation and the ionine in the same run. So if we have some surfactant into the mobile phase, you can even separate the neutral compound as well. So that is something like we talk about later. So for ion exchange, we mentioned that. So it really depends on so what kind of ion you can separate. Really depends on so what is the charge on the stationary phase. And for this one, now the fixed site on the stationary phase is what is negatively charged. So that's why you're going to retain, is going to attract so the positively charged ion. So that's why if the stationary phase is negatively charged, it's called cation exchanger because it's going to attract cations, right? Okay, so before you load a sample, so and then we run the mobile phase go through, and then so there's some counter ions in the mobile phase. So those counter ions, so they have positive charge, so they can coat it on the stationary phase, and then so make it to be electronically neutral, right? And then so you inject the sample, and the sample analyte so gets in, so it's going to compete so with this counter ion, and it's going to displace them, and then so by binding with the stationary phase, right? Okay, and then so because different sample ions, if you have multiple compound, so they will have different charge density. That is very important. So property we look at later, we will mention about that. So different charge density, so and also different polarity. So make them to have different affinity to the stationary phase. Some of them can be more strongly bonded. Some of them have, say, more loosely bonded, not really strong so attraction to it. So it depends on the different affinity. So and the more strongly bonded one definitely will elute later. The more loosely bonded one will be eluted earlier, right? Okay, so then so this is how they do, and you run the mobile phase. And for the mobile phase to go through, how we can elute this analyte. So there's different parameters you're going to play with. So for example, definitely we can think about pH, right? So you can think about, we can also play with the different, so counter ion, okay? So different mobile phase. So, and then you can think about even so if we're using a diluted salt, and then so we can use different ion strengths, that means concentration. So the concentration of the counter ions, so the type of the counter ions, and also the pH, they all play a very important role about how fast they can be eluted, come out. Okay, all influence the retention, all influence that one. And then so after that, so you want to go back to original setting and then regenerate the column and for the next one. So it's quite straightforward, but already from that, you hear me mention different things. So mobile phase, the counter ions and charge density, pH, ion strengths. Now you know, you have some idea. So there are different parameters that can influence the separation in ion exchange chromatography. And later on, we'll go through that one by one. Okay, so for ion exchange chromatography, and the principle is like ionic analyte species, they separate on cationic or anionic side of the stationary phase. That means the stationary phase should be charged, definitely should be charged, okay? Not neutral. So, and either positively charged or negatively charged. So the separation is based on that. It's based on electrostatic interactions between the analyte and the stationary phase, right? Okay, so that means your analyte should have opposite charge to the stationary phase. So otherwise it cannot be attracted, right? So the variety of coordinates to support, so dynamically exchanged or permanently bound in the ionic group. Okay, so and it depends on so what kind of stationary phase you're using. So later on we should show that we classify so the stationary phase to be strong cation, strong anion, or weak cation and weak anion. So what does it mean for strong? What does it mean for weak? Okay, so that strong and that's weak indicate what? And the mobile phase is often an aqueous buffer solution. So, and for an ion chromatography, if you want to separate fluoride, chloride, bromide, often this is we're using buffer solution, so sodium carbonate and sodium bicarbonate mixture. So try to maintain why buffer? Why buffer? Because the pH actually play a very important role, right? So in ion chromatography, they're using buffer solution because you want to have it to have constant pH over a range of the the mobile phase concentration. So and then the migration rate of ions depends on the type and concentration of the counter ions in the mobile phase. Okay, so that means how this one can be eluted. So we'll talk about that. Okay. So retention time based on the affinity of the ions to the exchange site. Okay, and this one is very important. Okay, affinity really depends on the charge and also depends on their size. But when we talk about the ions, so in aqueous phase, those ions, because they are in water in aqueous phase, they are not showing in the aqueous phase as a bare ion. That's very important, okay? Because they are going to surround it by water molecule. So that's why each ion, so in a sample, they are actually hydrated. They're actually hydrated. So when we talk about the size of those ions, so we talk about the size of hydrated ion, not the ion itself. Okay, so later on when we talk about the charge density, so which is the ratio of the charge to the size, is the charge to the size of the hydrated ion. Okay, so and this is so determines the affinity. Okay, and also the competition between the buffer ion and analyte ion. So which is greatly influenced by ionic strength, that's concentration of this buffer ion, pH of the mobile phase, and so on. Okay, so and for the ions, so in the ion exchange chromatography, including anion and cation. So anion, negative charge, cation, positive charge. Also has mono, so di, trivalent. Okay, so and we I think mentioned a bit the cation, so can further becomes a inorganic metal. Okay, and also so there are earths, right? So alkaline earths or alkaline metal. So and then so and also ammonium. So this one we will often talk about sodium, potassium, magnesium, and calcium. So those are often analyzed, and also can be some transition metals. Okay, and for organic can be organic amines. So this one is also considered. But ionize can be like inorganic fluoride, chloride, sulfate, nitrate, nitrite, so cyanate, and so on. So many of them. Okay, and also can think about organic acids. Okay, so they are characterized, so including both organic and inorganic, anion and cation, or mono or polyvalent. So it's really has pretty wide application. Okay, so that is just simple, quickly go through of ion exchange chromatography. So what is ion exclusion chromatography? So we just mentioned the different kinds of IC. So ion exchange is the one we're going to talk about more in detail later on. Okay, so just quickly go through the principle. So we say in ion exchange chromatography, the charge of the stationary phase and the charge of the analyte, they are opposite. Okay, so they're opposite, so they can be attracted to each other and then retained by the electrostatic interactions. However, for ion exclusion chromatography, you can tell from name, is excluded. So the stationary phase now has the charge that is the same as the analyzed ion. So this is totally opposite to ion exchange. So you can see here, now the stationary phase, they have very high density of this ion exchange site, but also have the same charge as analyte. We say the ion exclusion chromatography often used for those, say, weak organic acids. So for those weak organic acids for this one, so therefore you can see here, so those acids, when they charge, they are negative charge, right? So it should be ionized. So that's why you can see the stationary phase now. What is the charge? The sulfonate. It's a sulfonate, and it has very high density of this negative charge, the sulfonate sites. So on the stationary phase, and because now, then before you run a sample, so we want the mobile phase to go through, then the counter ions. So in the mobile phase, they're going to coat it on the stationary phase to make them what? Make them electronically neutral. And for this ion exclusion chromatography, the mobile phase normally is just diluted acid, mineral acid. So it can be, say, diluted sulfuric acid and diluted, so this the hydrochloric acid. So that's why. So the ion used to, the counter ion that's used to cap. So this sulfonate group is just like hydrogen ion. So you can see here, because they're very high density of this sulfonate group on the stationary phase, so there's a lot of the hydrogen ion, so coated on the stationary phase. Okay, so, and this one is, we can see that. So, and also what you see here you can see some water here, particularly here. Okay, what happened? Because the stationary phase, this matrix, they are porous materials. So they have pores. They actually have like this one. So inside, and those stationary phase, they may like say could be coated inside. So the water, because your mobile phase is just like diluted, acid. Okay, so the mobile phase and the water so actually get into the pores, and then so they form those one is called occluded water layer. So it's actually the occluded water layer now here act as something like real stationary phase. Why I say that? Because now you can see here the mobile phase is the diluted mobile phase. So it has much more diluted hydronium ion. But here on this binding side, so they are very high density of this hydronium ion, hydrogen ions, right? So therefore the electric potential between this high exchange site stationary phase and the diluted mobile phase, so it's quite large. It's called the donor potential. And because it's those, like say, high density hydronium ion and stationary phase, now they have this tendency to diffuse from this high concentration spot to the low concentration diluted mobile phase. So they're going to diffuse here. So when they're going to diffuse here, what happened is like when the ions diffuse, so they just leave the stationary phase, so not neutralized. So when the proton, so this one, when the hydronium ions leave, so they will leave the stationary phase, so become not really neutralized, and then so instead, so become negatively charged. So that will be leave the stationary phase negative charged. So now the stationary phase is negative charge, which has the same charge as this weak organic acid. So what happened? Well, okay, so if the acid is very weak, so and because now you also have this mobile phase is diluted acid. Okay, so and then so that means you're already in the acidic mobile phase condition. So if it's very weak acid in this diluted acidic condition, so it will be in this neutral form. instead of ionized form, right? Okay, so it's a neutral form, then it's possible. It can diffuse into the water, but it will not bound here. Negative charge, no, right? Okay, diffuse in and diffuse out. So it takes time to go through the column, right? Okay, diffuse into the water. Okay, and however, if it's a kind of strong acid, organic acid, what happens? So it'll be charged. And what charge does it have? Negative charge, right? Okay, so for those strong acid ionide, can it diffuse into the water? Can it diffuse close to the sulfonate group binding site? Can it? No. Yes, very good. No. Why? Because this one has negative charge. So it's repelling it. It's a go away. So we have the same charge. So it cannot come here. I'm not attracting you. So it's totally excluded. So it cannot even diffuse into the water and come out. It's just like expelled, right? So, and then this one, actually the strong acid, the charged one, it comes out fattest because total repaired, it won't diffuse in, diffuse out, it directly go. Okay, so it will be the first one to come out. And for those weak ionized one, which for those one not that weak, for some in between, some of it can be charged and a portion of that is the neutral form. So, and because depends on the dissociation of this weak acid. So, and then, so you have different, say, diffusion and retention into this water layer, and then it will comes out in between. So the neutral comes out, the neutral molecule can enter the excluded, occluded water layer. So they comes out lost, okay? And the very ionized one, strong acid one, that comes out first because they're totally expelled. And then for those weakly ionized analyte, so they separate based on their extent of ionization. So they'll be in the middle. Okay. So for those that very weak one, definitely comes out later. But I say more, say easy ionized one, so they comes out so faster, right? Okay, so really depends on the ionization. So this is how that works. So, and this is how those carboxylic acids, so those organic acids get so separated. Normally, so it handles the organic acids in a which has a pKa value between 2 and 6.5, so it can do that. So that's also the reason why the mobile phase using diluted acid to make the mobile phase. Why? Because for some of those weakly ionized analyte, if it's in the diluted, so acidic medium, so that can make them more become neutral form, and then so they can have a longer retention. Understand? So that's how it works. So ion elution chromatography. Okay, so far okay. So if no problem, so we move on to next one. So ion pairing, we actually have talked about that already. Okay, we talked about the mechanism, the two mechanisms for that, right? So then here we're going to quickly go through. So for ion pairing, now the stationary phase is not charged. The stationary phase is not charged. For ion pairing, the stationary phase, they are hydrophobic neutral one. Normally it's C8 or C18. Okay, so ion pairing is actually, we use a reverse phase column to separate metal ions. How to do that? And then, so that's why, so because now you have stationary phase is hydrophobic. So that's why we need to add ion pairing reagent into the mobile phase. And this ion pairing reagent, normally they have a charged head and hydrophobic tail, okay? So it's often hydrophobic ion, and the head of it, so agent. So the head of it has the charge opposite to that of the analyte, okay? Like this one, now the analyte is the metal, which is positive, and then, so the head of this reagent has the negative charge. And then, so there are two mechanisms we mentioned that. Either, so they already form, so are kind of the complex in the mobile phase, and then, so I form hydrophobic tail of this newly formed compound, we just like partition onto stationary phase, right? This is one mechanism. The other mechanism is like, say, now, So for this ion pairing reagent, so first, so its hydrophobic tail will just like say bind to the C8 or C18 column, so stationary phase because hydrophobic. So and then so it has its negative head pointing outside. So that makes the reverse phase stationary phase looks like a negative charged ion exchange column, right? Okay, so to become negative charge pseudo because it's not real, but it looks like that one. And then so you'll attract the metal based on electrostatic interactions. So there's two mechanisms, I mentioned that before. Okay, so just quickly go through. So and I see here the ion pairing agent associated with stationary phase and functions as ion exchange functional group. This is a second mechanism. So we mentioned earlier. Okay. And normal the ion pairing agent for this metal separation. So they are so the C8 so sulfonate. So it is the C8 this hydrophobic tail partition to the reverse phase stationary phase, and then and the metal ions in your analyte so is attracted to the negative charged head of this ion pairing. This is sulfonate group, okay, reagent, and got separated. And then used especially for large and hydrophobic analyte, so they have slow mass transfer or secondary hydrophobic interactions with the typical ion exchange stationary phase. So, okay, so that's all for ion exclusion chromatography and ion pairing chromatography. Now we come back to ion exchange chromatography. Okay, so for ion exchange chromatography, we mentioned about, so it can separate into ion exchange and cation exchange. So ion exchange column, so it's going to retain ion. So the stationary phase should be positively charged to attract ion. Okay, so and cation exchange, you're going to retain cation. So the stationary phase need to be negatively charged to retain the cation. Okay, so and there are generally 4 types of this ion exchange chromatography, so which are strong cation, strong ion, weak cation, or weak ion. So what are the strong cations? Strong cation refers to sulfonate group, and strong ion refers to quaternary amine. So why we call them strong? Because they remain charged over the common pH range in the IC analysis. So they just remain charged over the pH range from 0 to 14. Okay, so they're so that's why we call them strong. So they just always keep like charged. So under normal analytical condition. And say, how about we say weak one? So weak ion, weak cation. So for weak cation, there's several ones. Carboxylic acid is one of the type of weak cation, but phosphoric acid, others as well. So that means, and I have mentioned this one, and for the weak ion, should be positive charge, right? Stationary phase can be tertiary amine, secondary amine, and primary amine, okay? We call them weak. So that means their pH, so that means they're not really, remain charged over the whole pH range. So that means they can lose their ionization, so as a function of pH. So it really depends on the pKa value of the corresponding acid or base. Okay, and we mentioned that. Let's see. So this one shows the type of functional group. Normally encountered. And you can see the type functional group. Let me see here. Determines the type of strength of ion exchanger. That's 2, because determines whether it can retain cation or ion. So whether it's strong or weak. So the total number and availability determines capacity. That means how many of those charged sites on the stationary phase. Okay, and this is pretty common. So that's what I just showed you guys. And then if we want to look at the details of them, So you can see, so the ion exchanger are characterized both by the nature of the matrix used as support. Later on, very soon, we'll talk about it. So what matrix can be silica-based matrix or polymer-based matrix. Okay, and if you have ever heard that one for ion chromatography, actually we normally use the matrix called the resin. Okay, and also it really characterized by the nature ionic functional group on the surface. So, and let's look at this first column. So the first column, current exchanger, only the first one is the strong one, okay? Only this one's strong one. All the remaining in this column, so they are the weak current ion exchanger. So what are they? The carboxylic acid, phosphoric acid, phosphinic acid, phenolic acid, and even can be some inorganics. So this arsenic, xenonic, okay? So, and this actually carboxylic acid and phosphoric acid more often used, okay? So we call them weak. Why? We say that because they can be either charged or uncharged based on the pH of the mobile phase. If you still remember that, do you still remember that for the weak acid, pH equal to what? pKa plus log what? A negative charge of conjugated form over its acid form, right? Okay. So for example, so if you have now the carboxylic acid, the pKa value is equal to 4. So, and then now if you have pH equal to 6, can anyone let me know now the acid is in a charged form or a neutral form? Which form it should be? In the charged form or neutral form? If now you have pH equal to 6 and pKa for this carboxylic acid, so its pKa value is 4. Now you have the mobile phase pH equal to 6. So now, so this stationary phase, carboxylic stationary phase is charged, is ionized, or neutral? Charged. Very good. Thank you. Okay. So because equal to plus, so plus 2, what does it mean? That means log. So conjugated over acid form equal to 2. And then that means what? That means HA equal to what? 100, right? Okay. So 100, that means it's many in which form? It's many in this form, right? Okay. So that's why you can see that if you have weak acid, so as the weak contact exchanger, if you want to keep it charged before you load the sample, you want running your mobile phase the buffer solution, so to have at least 2 units larger than its pKa value, so it can be charged, right? But for elution, how about for elution? So this one is for loading. So you want it to be like 6. So, and then make it charged. How about for elution? Now, if you want to, for elution, I want to change the pH and to get eluted out. And then, so what is the pH to be? Now the pKa value equal to 4. And what is the pKa value? What is pH value? If you want to, for elution, you want to break that interaction, want to make it neutralized, right? Okay, I see the answer. 2, very good. Okay, so you want to make it so and to be neutralized, and then so you have 2 units. Oops, sorry. And for elution, oops, you want to be 2, right? Because then you'll be 4 minus 2. So that will what? That means that one HA equal to 0.01, right? So that means the many will be the neutralized one. Okay, understand. So that is what we mean strong and weak. So I'm saying here for quaternary amine, so and this is a strong one. This is strong one. And for the remaining, we consider that to be weak one, especially the primary and secondary one, the really weak. Okay, the weak one. So and then so they need to be at acidic condition to make them to be charged, right? Okay, so and then so basic condition and then to make them to say for elution that one. Okay, very good. So that is the concept for that. So now let's come to the matrix. This is the nature of the ionic functional group. So ion exchanger categorized by the nature of ionic functional group based on what charge they have and what they are. Okay, but also depends on the nature of the matrix as support. So what is the matrix we often use for ion exchanger? The ion exchanger consists of an insoluble matrix to which charged group have been covalently bounded. So this insoluble, that means it should be stable under this acid and base condition, right? Okay, so it should be stable, it should not be soluble, and could be silica-based or synthetic organic polymer based or hydrous oxide. Because the first two are more commonly used, so we are going to just talk about the first two. So, and the silica-based matrix, so, and there are two distinct groups of this kind of silica-based material. So one group includes the functionalized silica. Okay, so what is that? So where a functional group is chemically bounded directly to the silica particle. Okay, so and such as quaternary amine, so bonded to the silica particle, and then make it to be strong. So ion exchanger, and then so or alkyl sulfonate group bounded to the silica particle, because the silica particle, it has what? If you still remember, we mentioned about that. Solanol group, right? So it's this one to be chemically derivatized to make them to have this chemical bounded so stationary phase. And for this one, because there are many of the solanol group available, so then so the number of the stationary phase that can be chemically bounded relatively large. So the capacity, because the more available stationary phase and more sample it can handle, right? So and then so therefore the capacity is moderate to high. Okay, so that means say later on if you're using conductivity detector, and then we have to use suppressed IC. Okay, now we're not talking about this one, just for information. So you think about it. Later on we come back to look at this one. Why we say you have to use suppressed IC. So this is for the functionalized silica. So another type of the silica particle is polymer coated silica. So what happened this one? So here, so the silica particles are first coated with the thin layer of polymer, such as polystyrene, silicon, or fluorocarbon, and then this layer is then functionalized. So you may ask, why not just using a polymer here and then so and directly do that? Okay, because here it has some advantage, because just if you're using a thin layer of polymer here coated on the silica, and then there'll be faster diffusion so of the solute, so through this thin layer of polymer. So and if a fast diffusion, we say if a fast diffusion from what we know from the HPLC already, right? If the diffusion coefficient is faster, that means they can reach the mass equilibrium faster. So it'll be faster mass transfer between the two phases, and then that can lead to a better efficiency of the separation. Okay, so and for this one, however, it has low capacity, so that's why. So and no need to use the suppressed IC. So overall, when we talk about the silica-based matrix, so it has its own advantage. So it has pretty good chromatographic efficiency, and also because the silica particle is quite rigid, so it has a stability and durability under high pressure. Okay, it's quite stable and durable under high pressure. But we all know, so the silica particle, it has its biggest drawback. So this one, I actually have mentioned that for several times before, right? So what is that severe drawback? It's because it cannot tolerate very acidic or very basic environment. So it has very limited pH range, so over which the silica colony can be operated. Normally say, as I say, can be 8 actually. So from 2 to 8. Okay, so remember we mentioned about for the mobile phase, like we can use sodium carbonate, sodium bicarbonate. So that mobile phase already have pH of 10. And then for sometimes we can even use sodium hydroxide. And then so that pH can even go up to 12. And then so that is a way larger, higher than silicon particle can handle. So obviously this silicon particle, so based matrix won't be suitable for that. Okay, so this is one very severe drawbacks for this solid silicon-based particle matrix. Another drawback is because there are many of the cyanonyl group. If you remember that when we talk about partition chromatography, not all this cyanonyl group can be derivatized. So maybe 50% is pretty good already, right? Okay, so there are many of the cyanonyl group, they're not derivatized. So therefore, so they're just like showing on the surface. And then what happened is, so and some of the high charge, the metals, such as transition metals, so they can what? So they can attract it to this free cyanonyl group, okay? And then so they are irreversibly absorbed on the surface, so which cause interference with the analysis. So, and that is another drawback. And because of that, because of the limitation of this silica-based matrix, so that comes to the development of this polymer-based matrix. We can also call this one as the resin, okay? So what is that? So you can see here. Now the matrix, they're produced by chemically derivatization of synthetic organic polymer, and they are the most widely used type of ion exchanger. So from that, so what is the normally used one? You can see it here's the structure. So what happened for this one, for this support? First, so the resin, so this matrix, they are synthetic to achieve the suitable physical and chemical property. And then, so they are chemically derivatized to have the functional group. Okay, so most of the ion exchange resin are made from copolymer, consists of the styrene, the polystyrene, here this is polystyrene, and divinylbenzene. So it's called polystyrene, PSDVB. PSDVB means polystyrene and divinylbenzene. So this one, so they form what? So you can see that they form the copolymer. And then sometimes also they consist of copolymers of divinylbenzene. This one still kept, and with some acrylic or methyl acrylic acid. So, but halfway from here, you can see that because of divinylbenzene, it form the bridge, right? So top and down, it's kind of the amount of divinylbenzene kind of determines the degree of cross linkage of this polymer. Okay, so if you have more divinylbenzene, so in this polymer, and then so it has smaller pore size, right? Because it may be more so highly cross-linked, right? Okay, so but if you look at the structure here, so even you have the chemical derivatization charge functional group on it, but if you look at the matrix, there are so many aromatic here. Aromatic is an N here, okay? So that means, so a significant portion of the surface area of the resin, they just like exist as a neutral polymer. They're not really or derivatized. So many aromatic moiety. And because of that, what happens? So they mean because they have this one aromatic functional group, which is hydrophobic. So that's why. So some of the reverse phase character of the original polymer will retain. And then what happened is, so if you are separating some organic ions, and the surface adsorption may contribute. They may have not only electrostatic interaction, but also have the secondary interaction, which is from this hydrophobic interaction of those organic ions and the stationary phase. Okay, so and because of this one, so this is the also makes a difference in the ion exchange selectivity between the resin and silica-based ion exchanger, especially for those organic ions, because they may have this hydrophobic, secondary hydrophobic interaction with this uncoated station phase and resin. So, and to help to solve that problem, so when you're using a resin to do analysis, sometimes people add organic modifier, so into the eluent. So that makes some of the organic ions more soluble, so in the mobile phase, and then so can be more easily get eluted out. Okay, so to control that selectivity. So if we make a comparison of this silica-based and resin-based matrix, so the primary advantage of the resin-based ion exchanger is their what? The tolerance over a wide pH range is the biggest advantage. So it now can tolerate so a much wider pH range than silica-based matrix. Okay, so the sample with extreme pH value between 0 and 14 now can be handled in this polymer-based matrix. So however, silica particle, I mentioned that it can only handle 2 to 8. So, and then the wide range of pH can handle in by the polymer-based matrix, make it to be able to expand application of IC to those multi-charge or weakly ionized analyte solute. So therefore, we mention that a polymer-based separation column is the only option for suppressed ion chromatography. Now you may not really understand what it's talking about. Let's keep it. Let's come back later when we are talking about suppressed ion chromatography. And we see what does it mean. Okay, so. And however, there's some limitation for this polymer resin as well. So because they're relatively soft, right? Because they're just like say those synthesis polymer cross linkage, right? Okay, so they are subject to pressure limitation. So they're not as rigid as silica particle. They're relatively soft. So and then so therefore the column lengths and flow rate, they are limited. They cannot really handle so very long column, large pressure drop. Remember, we said the pressure drop delta P proportional to what? So if we still keep the mu here, length here, and then so we'll dP square. But if we replace that mu by dm dP, and then so here will be dP triplet, right? Okay, so the pressure drop relate to the flow rate. The larger the flow rate, a higher pressure drop. The longer the column, the higher pressure drop. The smaller the packing particle, the larger the pressure drop, right? Okay, so that's why, because this limited pressure, and then so that's why you cannot have a very large L, and also you cannot have a very large flow rate. Understand? That's the reason. Okay, but if we use a macroporous resin, so that can be relatively more rigid and stable, and then so for that one, then can use for a longer or common higher flow rate. Okay, so that's for that. And then if we talk about the capacity of IC, it's very similar to what we talk about for our HPLC. So we are talking about capacity, K, efficiency, right, N, and also selectivity, alpha, right? Capacity, efficiency, and selectivity, right? Okay, so probably we just take a break here. So we come back at so 55, and then we can continue. Okay. Okay, so let's start again. So we talk about capacity. So capacity is the retention time of the ions and the ability to accommodate sample with a large span in ion concentration. So that's a key value, right? We talk about that one. So capacity really, so and also relate to the number of functional groups. So the number of functional groups, I would say, so the more site available on the stationary phase, and then the larger sample you can handle, right? Okay, so but however, the problem is like if you have a larger, higher density of the binding site, so then you have more sample, and then you have to stronger mobile phase for elution. You have more like higher concentration of salt concentration, higher the concentration of the mobile phase for elution. And then so that if you're using conductivity detector, actually that provides a burden, unnecessary burden to the conductivity detector. Okay, we talk about that. For efficiency, that means also you want to achieve high efficiency, high n number, and then because of high efficiency and resolution, because of resolution, this one we already talked about. So proportional to square root of n, and then you have better resolution, you have a higher and narrow peak because of height, right? Okay, so peak height proportional to that one, right? And then so you have good sensitivity. And selectivity also is what we try to achieve. So selectivity based on, so shows the different, the relative affinity of the stationary phase to different ions, right? Okay, so there are different parameters that can influence selectivity, including so those parameters of the analyte ion, the mobile phase, the content ion, and also stationary phase as well. Okay, so and we should need to aim for the enough selectivity so to achieve separation between different analytes. So capacity. So if we talk about capacity, the ion capacity of ion exchanger is determined by the number of functional groups per unit weight of the stationary phase, normally expressed as the milli equivalence of charge per gram of dry packing, or milli equivalence per milliliter of wet packing. Okay, so it plays a significant role in determining the concentration of competing ions used in the mobile phase elution, because the competing ion content ions, so they have to have the stationary phase to reach our electronic neutrality, right? Okay, so and higher capacity stationary phase generally require the use of more concentrated mobile phase. That is sometimes not necessary. That requires unnecessary strong eluent. So that can cause problem. Why? Because if we're using conductivity detector, conductivity, that means then, so all the ions, they're conductive. If you're using the mobile phase, which is a salt, which is an acid or base, so your mobile phase itself is conductive, right? And if it require you, if you have a more concentrated mobile phase, that means like say more ions in your mobile phase, and then you have even higher background in this conductivity detector. And then so that background is too high, and then so that causes problem. And then even you use the suppressor, so they put the burden, a pressure on the suppressor to remove the signal or response from the mobile phase from background. Okay, so that's why you don't want too high capacity. At the same time, you don't want the capacity to be too low. Why? If I have it too low, and then so it's very easy for your column to get overloaded. So and you got very small dynamics range, right? Okay, and then so and that could be difficult to handle. So a typical ion exchange capacity of IC is normally 10 to 100 milli equivalent per gram. Okay, and for that one, when you load a sample, also you don't want it to be exceed 5% of the total capacity. Okay, so well, if you're talking about selectivity, so selectivity really depends on so many different factors. The relative, it means the relative affinity of the the stationary phase to different ions, right? Okay, so it's quite complicated, but it's still possible to provide some approximate guideline to judge or to tell this relative affinity of this ion exchanger to different ions. And normally we have to consider the properties of the solute ions, the mobile phase ions, and the counter ions. And the most important thing I have to say is charge density. So which is a charge on the solute ion, also the size of the solute ion. So this ion solvated is, so yeah, if you're talking about counter ion, it'll be the ion, so charge density, so solvated ion. Because as I mentioned earlier, when the ion is showing up in the aqueous phase, in the sample, in the mobile phase, they're not showing up as a bare ion because they are charged, okay? So they're in the aqueous phase, they're surrounded by water molecule. So they are all showing up in the hydrated ion form. So when you talk about the size, you have to think about those hydrated ion. Okay, so and also it's talking about the degree of cross-linking of the ion exchange polymer. Remember I showed you this one before I showed the polystyrene and DBB, right? I said the more DBB has, it has higher degree of cross-linkage and then it has smaller pore size. What happened if a small pore size? What happened? If you were dealing with those ions that has relatively large solvated diameter, and then if the pore size is too small, they cannot get in, they cannot diffuse in and bind with the stationary phase, right? So this one, if a very high degree of cross-linkage, so that may cause some unwanted ion exclusion thing, okay? Ion exclusion effect for those large ions. So then this one you have to think about, okay? And also there's the activity affinity to ionide also depends on the polarizability of the ionide. Often like say if you have something like the higher charge and the smaller size, so they are more polarizable, okay? So, and the more polarizable, that means they can stay high affinity, that means stay longer, okay? So, and also the ion exchange capacity of the stationary phase, see how much they can handle the concentration level, and the functional group, yeah, of course, right? And also extent of interaction with stationary phase matrix of the support. That means the one you don't want, the secondary, is the secondary, so interaction, which is we say artifact. Secondary interaction. Okay, let's look at it one by one. That's okay. First one, the charge density. So as the charge density of the solute ion increases, its affinity for the stationary phase also increase. So keywords, charge density, increase. So affinity also increase. That means it has larger K, right? Larger retention. And also keywords, charge density means charge over solvated ion size. Okay, so how do we do this one? Probably we do that whiteboard. Can you see the whiteboard? Yeah, you guys see? Okay, so now we do that. So how about we look at a group of ions? Okay, so how about I have fluoride, I have chloride, I have bromide, and iodine. Okay, so how about the radius of these ions? Can anyone tell me? From fluoride to iodide, so this is increasing or decreasing? Increasing or decreasing? Increasing or decreasing? Fluoride, very good, thank you. Thank you for your response. So it's increase this way, right? So increase. So it's increase. So radial increase. So which one has the largest charge density if we're talking about the bare ion? Which one? The fluoride, because same charge, but then the size increase. For fluoride ion, it has the larger charge density, so it's able to attract more water molecule to surround it. So it can attract more water molecule to surround it. So if we're talking about the hydrated radius, can anyone tell me? So hydrated fluoride, hydrated chloride. So which one is the largest radius? So is hydrated fluoride or hydrated iodine? So which one? Which way? This way. If we're talking about hydrated radius, so because then the fluorine, the ion, so fluoride, the bare fluoride, it has smallest size, same charge. So if the bare ion has the larger charge density, it can attract more water molecule to surround it, and then make it the hydrated ion radius to be largest. Understand for this sequence? And then now we are talking about charge density, which is the charge over the hydrated radius. Now, can anyone tell me? So which one has the largest charge density? Which one has smallest charge density? So which one has the smallest charge density? Anyone want to respond? So which one has smallest charge density? If we talk about charge density, so now is smallest charge density? Yeah, very good. Thank you. Is the fluoride, because now it's Z over hydrated radius. Z for them, the charge is the same, which is what? -1. Okay, so for this charge density, now we're talking about hydrated ion. So it's the charge density now is iodine has the highest charge density, fluoride has the smallest charge density. So this charge density reflects the affinity. So, and then, so can anyone tell me, so how about the retention, the K value for this one? Which one comes out first? Which one comes out last? Tell me the one that comes out first in the column, in the iodine chromatography. The one has strongest affinity or the one has weakest affinity? Which one comes out first? Which one? Which one comes out first? Which one has the smaller retention? Which one has the larger retention? Very good. Thank you. Very good. Very good. So, okay. So then, so that means fluoride comes out first, followed by chloride, bromide, right? Okay. So like this way. So here, this is the first one to come, and this will be the last one to come, right? Okay, because it has stronger affinity. And then iodine and fluoride has the weakest affinity. Okay, so that's why it comes up first in the column. And then, so elution order will be fluoride be the first. Understand now? So how about we do that for another group? This is for iodine. So let's do that for cation. How about change the color? Oh, sorry, eraser. Okay, so let me change that to this one. So how about, oops, lithium. Okay, alkaline metal, sodium, and then potassium, rubidium, and also have cesium. Cesium. Okay, cesium. Okay, so how about the radius? How about the radius now? Again, radius, which one is smallest for the bare ion? Again, lithium smallest, and cesium ion largest, right? So radius also go this way. And however, now for the bare ion, so the radius for lithium is smallest, so its charge density for this lithium ion is larger than that for potassium, right? For sure. And then so it can attract more water molecule to surround it. So if we're talking about its hydrated radius, and then because it's attract more water to surround it, we go this way, right? See it? Okay, follow, right? Okay, and then so how about now charge density? The charge to the hydrated radius. Which way? because now the hydrated radius, ion radius for lithium is the largest. Now the same charge, positive charge. So it has largest R, and cesium has the smallest R. Z is the same. So that's why charge density is increasing from hydrated lithium ion to hydrated cesium ion, which is also means affinity, reflect the affinity. And then, so how about the retention? Again, anyone can tell me which ion comes out first in the kind time chromatography? Which ion comes out first? Which one? Very good, thank you. All correct, your answer. Okay, so and then the lithium comes out first and cesium comes out last. Now, do you understand now? Okay, so very good. So now let's stop this one and we come back this one. Okay, now can you see my screen, right? Okay, very good. So we come back to this one. Let me think. Okay, so I'll just use this one. It's fine. Cancel. And then so my notes all gone. Don't matter. Okay. Interesting. Oh, come back. Great. Okay, so and this is how we tell the affinity elution order, the K value. Okay, so you can see this is really charge density matter, but it's a charge over the solvated size of the ion. Okay, the high charge with smaller solvate ion radius result a higher retention because it has what? A higher Coulombic interaction, so it has a higher affinity. So it can be more pronounced in more diluted mobile phases. Okay, so if everyone understand, we move on to the next slide. Okay, so you can see here, this one shows you exactly what happened. Now we have the positive charge, the beads here, positive. So it's going to return, so the negative aniline. Okay, now it's protein mixture. So, and you load a sample, and those neutral and positively charged protein, they comes out at T0. They come together with the mobile phase. No interaction at all, right? Okay, and then, so this is for small negative charged one, large negative charged one. So the larger Z, and then, so if assume the same size, and then so comes out later. So you can see that. So this is the one example for that. And you can see again, so for the less charged molecule, so and or also say for those with smaller charge density, so they bind less strongly to the rhythm, and the equilibrium with the moving mobile phase rapidly travels rapidly and comes out sooner, smaller K. Okay, and for those has higher charge, smaller radius, say we have those, for those who have charge, higher charge density, so they comes out latest here, latest. Okay, and then so more tightly because I have strong affinity, and then so and they travel slowly and eluted later. Okay, so generally we can kind of predict the affinity for the stationary phase of different ionides. For different ionides, first rule is trivalent ions has a stronger affinity than divalent one and high affinity than the monovalent one. A3 minus larger than A2 minus larger than A minus. Okay, so the charge density, so the first thing is charge density. Okay, even the charge itself already play very important. The second one, you have to think about polarity. Okay, So, oops, you see that for same group, we can already see. So this one, OH, has the weakest affinity. So that means this is the first one to come out. Fluoride, right? Okay. So fluoride, C chloride comes later on it. Bromide, strong affinity. Iodide, strong affinity. You can see this for the same group. You see that. So how about it with others? Okay, so with others, we can see. So when polarity, not really, sorry, no, polarizability, I should say. Polaride is not really polarizable. It's not polarity, polarizability. So when charge density comes increase, and then the retention increase. When polarizability increase, retention increase. Okay, so I have to say this kind of illusion order, so affinity order, may not really fixed. Okay, so it really also depends on your mobile phase. Okay, so it's just roughly get idea. It's not really always like this order. Okay, so and it's just like say give you some idea. So this one definitely you should know that this one can be influenced by what? Can be influenced by pH, definitely, and then so, and ionic strengths. And also the competing ion, right? Competing, so ions, those kind of things can influence that. Okay, so here you see that. And then already we can see this is charge density play role, and you can see here secondarily charged. You see A2 larger than A minus, but why I see this one is monovalent? Why is here? It's talking about polarizability. Okay, so this is also because the polarizability influenced that. And there are different things, like say, because you can also see the same charge. So, and sulfate, so affinity stronger than sulfide, right? And then for nitrate, sorry, not really, no. Nitrite. And then what else can we see? That this one, at least in the list. So they also because of the polarizability. Okay, also same here. Okay, the larger polarizability, the larger retention. And also there's a series of that one. Let's see, how can I show it? And for another group, whatever here, if I can see, I can probably see more space. This is a perchlorate. It has stronger affinity than, oops, sorry. The chlorate, stronger affinity than chloride, stronger affinity than hyperchloride. And also it's because of, even they have the same charge, and then it's also because of polarizability, and then so, and the polarizability of the perchlorate larger than this chloride, chloride, and then hypochlorite. So if we put that into here, so, and this one, so it's here. So, and then sulfur cyanate, even strong affinity than that. And then so ClO4, this one. Then the perchlorate has even stronger affinity than sulfur cyanate. Okay, so you may wonder what is A3 minus. A3 minus you often encountered, let's go here. And because there's someone even larger than that, then there'll be that one, it can be the citrate. the citrate ion. This one is even larger affinity. So for the citrate ion, so it has the C6H5O7. I want if we redraw the structure, so inside. Okay, and now here, 3 carboxylic group. Okay, 1, 2, 3. Okay, carbon 6. 1, 2, 3, 4. I'm sorry. 1, 2, 3, 4, 5, 6. Okay, so it has C6H5O7 and it's 3 minus. This one is a citric acid. This is citric. So this one is A3 minus. So it has the largest retention. So, well, this is basically what could happen, but for the same group, you can see they follow, so the order we talk about. Fluoride, smaller affinity than chloride, and bromide and iodide, right? Okay, so this is what you're expecting. And also here, pay attention here, you can see that. Yeah, so this is the dihydrogen phosphate, and then this is a hydrogen phosphate. Okay, this is 2 minus 1 minus. So this one comes out later than this 1 minus. And the phosphate, if a PO3 minus, comes even later, right? Okay, that all makes sense. So this is for ionize. And there's some general affinity order for, say, of those cations. And you can see, pay attention here. For cations, the difference between the trivalent, divalent, and monovalent even more obvious or stronger. Okay, so than that we see in ionize. So you can see, like say, general rule, trivalent, they have much stronger affinity to station phase than divalent one, than monovalent one. And among this monovalent one, did you see the one that familiar to you? Lithium, sodium, potassium, right? Okay. Cesium will be lithium, smaller affinity than sodium, then potassium, and then cesium, right? So it comes up first. Lithium even comes up first before the hydronium ion. So this hydrogen ion, okay? Ammonium here and then. So monovalent comes up first. Okay, so the smallest, then this one lost, trivalent one. So and then how about the divalent one? Include those alkaline earth metal. So magnesium, calcium, and here also some transition metal, zinc, copper, cadmium, and lead. Okay, so they're already pretty strong. The alkaline earth metal already pretty strong binding with stationary phase. Very strong, pretty binding stationary phase. And then this one's more straightforward, more dominant by those charge. Okay, so that is the roughly, so this kind of illusion order. Okay, so and then so this is what we see. So for a real example, so this is a real example for the ionize. Okay, so fluoride, so chloride, nitrite is NO2 minus, bromide, nitrate, phosphate, and sulfate. Here, phosphate is not PO3, okay, PO43 minus, it's hydrogen, this one, okay, this, oops. Okay. How did I get enlarged this one? Interesting, huh? Okay. Okay, so, and this is the hydrogen phosphate, okay, it's not really, so this one is the number 6. It's hydrogen phosphate 2 minus. You can see now the colon. What is colon? AS4. This one is the highly cross-linked, so quaternary amine. So this one is the strong ion one. So it's a strong ion coordinate. It's a quaternary amine. And then, so can you see the mobile phase now? The mobile phase is a buffer solution. It's sodium carbonate and bicarbonate. Okay, so sodium carbonate and bicarbonate. And this is flow rate. And then you use suppressed conductivity. Suppressed conductivity. Now you can see the single charge one comes up first, and then followed by the divalent one, and follow that fluoride, chloride, nitride, bromide, nitrate, and hydrogen phosphate, and then sulfate, right? Okay, so this makes sense. So, and then how about the cation? And this is one example: lithium, sodium, ammonium, potassium, 1, 2, 3, 4, right? Okay, so they are what? They're monovalent, and then 5, 6, they're magnesium and calcium. Okay, so again, the magnesium, calcium, the divalent one that comes out after that. This one, because now it handles both. So the alkaline earths and alkaline metals. So this one generally have a stronger affinity to the colon. So then the single charge one. So you cannot using a very strong character exchanger. So you have to use the weak one. So this one is the weak one colon. So it's actually a mixture of the carboxylic acid and phosphoric acid. And also the stationary phase here is the methyl sulfonic acid. Okay. Sulfonic acid. Oops. Okay, my pen. Hold on. So, okay, and then and this is how it can handle. And then so also use suppressed conductivity. Okay, and to do that. So this just gives you some idea about how that works. And then so that is for the ions. So how about the property of the mobile phase? The property of mobile phase, they also play a role, okay? Because elution strength of the mobile phase, so we know that I already mentioned that, it's controlled by changing the ionic strength of the mobile phase, the pH of the mobile phase, and also the type of the competing ions, right? So, and the mobile phase used in ion chromatography are typically aqueous, so aqueous buffer solution, or like say aqueous acid solution, or aqueous alkaline solution, right? So, and really they can be, when we talk about property, so there are different ones where we can think about. The first one is the compatibility with detection mode. So should we use suppressed mode or non-suppressed mode? This is actually the most important one, the key one, okay? So it depends on, are you in suppressed IC or non-suppressed IC? Most of the time nowadays, the IC we use is suppressed IC, okay? So also the nature of competing ion, so that play a role. So, and the concentration of competing ion, that's ionic strength, mobile phase pH, already mentioned that. The buffering capacity of mobile phase, of course, then that's why you have then the sodium carbonate and bicarbonate, that's a buffer, right? Because we know the pH of the mobile phase can change the nature of some ions as well. Like for example, this was such a example here. Okay, now it's about pH equal to 10. So it shows the hydrogen phosphate ion. How about if pH equal to 6, something like that? And then will be definitely dihydrogen, right? Dihydrogen phosphate. How about pH goes to 13? How about pH goes to 13? And then so you further lose one hydrogen, become phosphate. So if it become phosphate, if that pH further increase, if it become phosphate, that will be PO4 minus. And then it will not, and then its nature changed. And then it will not come between nitrate and sulfate. It will come after sulfate, right? Okay, so that's why I say the pH of the mobile phase is important because it has some buffer capacity, and then so some of those multivalent ions, so they will keep the original nature, not really change to another one. Okay, and also the ability of complex the ion sample component. And this one is particular for transition metal. So for this one, sometimes you have to add the reagent, complex and agent to form some complex. So, but once that complex formed, that may change the original charge, and degree of ionization, and then the newly formed complex, they have different, say, affinity, retention to inner column, and so on. Organomodifier, we mentioned that earlier, right? We say like sometimes if you have secondary interaction, you can think about adding some of the organomodifier. So usually it needs to be water miscible, okay? So it should be water miscible. Don't worry, we'll talk about that. Miscible organic modifier, okay, such as methanol or acetylnitrile and so on. So all this will affect the retention order of analyzing ions. So that's why whenever you do that, so you have to always use a standard solution. So with on identity concentration and on your column to do the calibration and then to see the elution order. Okay, so the first one, the most important one, is compatibility with detection mode. So the detector signal obtained by the background, that is mobile phase itself, must not be too high. Otherwise, that will influence the signal to a noise ratio. If you have background very high, that means you have very high noise. And then so the overall, and signal to noise ratio. That means you have high noise, and then overall this one will decrease, right? That is not what you want. You want a high signal to noise ratio. So, and also that will influence the linearity. So very limited dynamic range and no stability baseline. So when high sensitivity is needed, so the highly responding mobile phase should be avoided. So that means if you're using a conductivity detector, and then so you want to remove that highly responding mobile phase signal, we're using suppressor. Okay, so and otherwise the signal for mobile phase need to be suppressed. So using suppressor and so on. So that is the idea for that. Okay, so and how about the nature of competing ion? When you talk about competing ion, it's similar to what we think about the sample ion as well, right? So we also think about affinity. So, and affinity also governed by the charge density, okay, the charge density. And the charge density involved the charge and also the radius and also polarizability as well. And the mobile phase ion of high affinity to stationary phase are considered to be stronger and will result in lower interactions of the sample ions. For example, carbonate, bicarbonate, they are stronger mobile phase ion than hydroxy ion. Understand why? Carbonate and bicarbonate ion, they are considered to be a stronger mobile phase counter ion than hydroxy. Understand? Okay, so sodium carbonate, bicarbonate ion, stronger than the sodium hydroxy. Okay, so that one, if not talking about pH, okay, if just talking about this one, the competing ion. So, and also the concentration, the higher the concentration result in a stronger competition, and then the retention will decrease, right? Okay, so and competition between the singly charged ion are generally more pronounced therefore. I'll show you, you'll see that from one example. So here is the desorption of negatively charged analyte from the ion exchanger. If we increase the salt concentration, you can see that. So here we will have low salt concentration, medium salt concentration, and high salt concentration. And you have negative charge protein, single charge, divalent charge, and trivalent charge. Analyte with low lead charge are eluted. So at medium salt concentration, this one. So whereas analyte with high lead charge require a mobile phase with higher ionic strength for elution, that one. So that means if you increase ionic strength, the concentration of the competing ion. So that increase the elution power of the mobile phase as well. And this is something like you can see here. So I just show you one, and this is for the analyzing of fluoride, chloride, nitride, and hydrogen phosphate, bromide, nitrate, sulfate. You can see that. So with increasing ionic strengths, the K value decrease for everyone. Decrease, okay? So it's decrease for everyone, right? But obviously we can see that for those divalent one, they're more sensitive. Their change is more sensitive to the change of ionic strength than those monovalent one. And the elution order of this cell and hydrogen phosphate, this one can even change. So when downstreams so changed from 2 to -3 mole per liter to 3 or 4, so to 4 and times 10 to -3 mole per liter. It can be 4. So I want a low ionic strength. So this one, the hydrogen phosphate, this one comes out after nitrate. Okay, and now when this one, the increasing ionic strength is more sensitive to that change, to this change, more sensitive and deeply decrease. So and then so it comes out before bromide, right? You can see this is how that change. So now how about the pH change? pH change we just mentioned. So equilibrium constant, we have to look at the pH and pK. pH and pKa, and here use minus, but you can, because the acid for over, because if it's plus, pKa pH equal to, for weak acid with base, pKa plus log A minus over HA. Okay, so this is general understanding for that. Okay, so really, so we use the 2-unit rule, right? So remember what the 2-unit rule we're talking about. So and for pKa, for this weak acid, so when the pKa value is 4 to 5, that one. Let me see, I can have one. That's fine. I think I have one. Yeah, okay. So here I have some information. For example, so if we for different compounds, so if for the sample, and where should I write it? If I say for the if a sample is, let's say, compound, if it's aliphatic amine, so the pKa value is normally like 9.5 to 11, and then so if you want to elute it, elution, so and then so if for elution pH, because you want it to be eluted, so it's normally around 12.5, or it can be like say about 2 unit, 1 to 1.5, 11 to 12.5. Okay, so it should be more, say, basic than that. And then for aromatic amine, if it's aromatic amine, and then so its pKa value is about, say, if it's about 7, and then so it's some can be even lower, and then so here elution pH about 8.5, like that one. So and for carboxylic acid, for carboxylic acid, so the weak one, if it's about 5, and then so this one, and then so this one should be like, say, for acid now, if I want to elution, that means need to be neutral, right? So and then so about 3 or 3.5 should be enough. And if it's a phenol, which is also very weak acid, but it's carboxylic and sorry, around 8. And then so it's about dilution about 9. So and so that. So this is something like general for those kind of things. And sugar should be pH larger than 12 and 13 for that illusion. Basically, if we talk about this one, so for weak acid, when pKa equal to 5, we use the 2 unit. So and then so if we want to make it say to be charged, pH should be at least 2 units larger than that. So about 2 units. In reality, can 1.5. And then so the pH, if a no charge, so and then pH smaller than 3. So and if it's wanted to be charged, and then so for loading the pH 7, and if it wanted to be say and release, and then so it should be go here. And for base, for weak base, you can see that. So if a weak base pKa equal to 10, if you want to be charged, then it be acidic, and then so retain. So that's why pH less than 8. But if to be like released, more basic, and then pH larger than 12. It just gives some idea of that. So we talked about that already, so won't spend time more details for that one. And then for the K value, let's see, first K value of these inorganic ions. So you can see that if we keep the different pH but constant ionic strength, so what is that? What does that look like? Okay, so for this one, you can see that. So and when pH change, because this is the iodine, so which one is very, very typical, this one. So and we can see that when pH increase, and then the K value decrease. Although we say ion strength, but remember what is the normal mobile phase we use for this kind of analysis? Sodium bicarbonate, right? Okay, so or what? Or sodium carbonate, right? Okay, so it's bicarbonate on the carbonate ion. Then what happened is, oops, sorry, oops. Mistake, sorry. Sodium. So okay, so and then so and what happened is what? So yeah, so and then so when the pH increase in this buffer solution, and then which ion will be more? The carbonate ion, so will be more, right? Right? So bicarbonate, carbonate. So there's equilibrium, the switch to carbonate ion will be more, and then so you'll have stronger elution power than bicarbonate ion, right? Okay, because it's what? So this divalent, okay, so it's 2 minus instead of 1 minus, okay, this one, okay, so that's why it's strong elution power. So that's why so those ions here, so their K value decrease. Same here, if it's a sodium hydroxide as a mobile phase, if you increase the pH and then more hydroxide ion, and then so that's why, so even if you say try to keep ionics constant, it's difficult, okay? So then you can see the elution, the K value decrease. And pay attention to here, this one. So now it's still the 2 minus at 10, but well, later on, so if you keep increasing, so the increase in pH and then will be different. Just for your information, for this multivalent one, you really have to pay attention to the pH, because for phosphoric acid, PO4, okay, and for this one, it's first pKa1 equal to PO4 minus. So it's pKa value, this pKa value. For this first dissociation, 2.1, okay? So it's quite acidic, but however, for the dihydrogen, this one, and then so you further dissociate hydrogen 2 minus, and then this is 7.2, and then so hydrogen 2 minus, a further dissociate, you get this one plus phosphate. So this one is this one, 12.3. Okay, now the pH around 10 for this time, carbonate, bicarbonate. So what happens when pH equal to 10? So it's mainly in the form of hydrogen phosphate one. But however, how about if pH goes to, so it's even larger than 13. So what happens? If it's even larger than 13, then you further lose, and then the major one will be the phosphate ions, right? Okay, so pay attention to that, especially when you are using the mobile phase, the sodium hydroxide, that could be a problem. So if you're using a higher concentration of sodium hydroxide with increasing concentration, more hydroxy ion, and pH, if possible, to more than 13, and then and the elution order of this one will change because it may change to be dominated by the phosphate ion instead of the hydrogen phosphate. Okay, so yeah, that's one thing I mentioned about the pH of the mobile phase. So can even change the nature of the multivalent ions. Okay. So this is a choice of the eluent for ion chromatography. So, and the most often used one is carbonate eluents. Okay, so which is sodium carbonate and sodium bicarbonate. So, and then however, after they come out of suppressor, and then so because the suppressor is the one that's reason with capped with hydrogen ion, so they release and form the comes out suppressor will be the carboxylic acid. So carboxylic acid, this one. So for typical, the elute, when it comes out suppressor, and the pH is around 4. So not just due to this one, but also because many of this one hydrogen release out, and then so and it comes out with your alanite, and then so this one so cause the eluent everyone to become more acidic. Well, I will explain that later. No worry. Okay, and at this pH. So some weak acid alanite may not be fully dissociated. For example, acetic acid, and then so that may have lower sensitivity, and also the linearity may not really good. So hydrofluoric acid has the same problem. Okay, so if you're using carbonate eluents, so for those weak acid alanite, so they may not have good sensitivity. Okay, so if your target on those weak acid analites, so you may think about using another eluent, sodium hydroxide. In sodium hydroxide, after suppressor, water is formed instead of carbonic acid. So, and water has very low background conductivity. And then however, we use sodium hydroxide, so we normally using say 10 millimole. If it's 10 millimole, sodium hydroxide, so that is already corresponding to pH equal to what? 12, right? Okay, 10 to the minus 2, right? And then and it's very basic. So that's why you have to prepare them plastic bottle and protect from CO2 in the air. So, and then purge that with helium gas. And also because of the high pH of hydroxide eluent. So, and if you're using even higher, if you're using 100 millimole of that, already goes to pH equal to 13. And some will even use that 500 millimole if a higher, and then with a higher pH. And then so the retention order of something will be different than that of carbonate eluent because pH change. For example, we just mentioned for this phosphate one. So, and then there'll be many in the trivalent phosphate and elute will after sulfate ion. Okay, now here probably now you can answer my question, because now this is a typical eluent for ion chromatography. So carbonate bicarbonate, so standard carbonate bicarbonate, and here is like 10 millimole sodium. This one pH equal to 12, and this one pH around 10. Okay, so around that one. So, and then, so remember what we talked about at very, very beginning when we talk about the matrix I say, how about you guys? So leave it as a question now. What do we say? A polymer-based separation column is the only option for suppressed iodine chromatography. Now, do you know the answer now? Why? A polymer-based separation column is the only option for suppressed iodine chromatography. What does it use for the mobile phase? I just showed you. Sodium carbonate or bicarbonate, right? Carbonate, bicarbonate buffer solution, which has pH around 10, or sodium hydroxide, which has pH even larger than 12 most of the time. So the pH now is much more beyond the pH level range that can handle by silica-based stationary phase. So that's why the pH is outside the silica-based stationary phase can handle. So that's why only polymer-based matrix can work for this situation. So that's why the polymer-based separation column is only option for this suppressed iodine chromatography. Now, do you understand why now? Because for the mobile phase used for this typical iodine suppressed iodine chromatography, so they are too basic. Okay, see that? Okay, so and the eluent should be degassed daily by helium, and the eluent must be filtered to avoid having the column in it so clogged, and normally all solution are diluted 2 liter by DR water having conductivity less than something. Okay, so let me see, and now let's take a break for 5 minutes again. So we come back at 2056, and then so after we come back, probably before I talk about the next part, I'm quickly go through the topic selection of the oral presentation. Okay, so now it's break time for 5 minutes. Okay, so this is the topic selection. You can see that. Let me see. Make it smaller. Okay, can you see it? The bigger. Good. Okay, so that'll be April 6th. Okay, April 6th, the last lecture. And then so as I mentioned that, so we're supposed to have 10 groups, but now it got 11 groups. Okay, so anyway, these are the topic that's been selected. So topic 1, topic 2, 3, 6, 7, 9, 10, 11, 12, 15, 16. So we'll just go through from the order, from number 1 to number 16. Okay, so and application of high performance liquid chromatography in forensic analysis. Here is the student that selectively, successfully select this topic. Okay, I'm going to upload this online later. And then here's the second topic, clinic application of affinity chromatography. And then 3 students in this group. So that's why I put a star here. So we're supposed to have 4 students in one group. Okay, and for number 3 topic, so application of ion chromatography in food analysis. Oops, miss one S. Okay, and then so 4 students in this group. Very good. And then so number 6 topic, 2-dimensional HPLC in pharmaceutical analysis. Also 4 students in this group. Number 7, so application of gas chromatography in petroleum industry. Very good, 4 students in this group. And then so number 9, application of capillary electrophoresis in forensic analysis. We have 3 students in this group. And then number 10, determination of vitamins in foods by high performance liquid chromatography, 4 students in this group. So and number 11, so application of gas chromatography for the analysis of Chinese medicine medical herb, which is just 2 students in this group. So and then so number 12, this is the most popular topic, which is application of high performance liquid chromatography for Chinese medical analysis. And then so the group luckily choose this topic. So it's 3 students here. Okay. So and then so topic 15, forensic application of gas chromatography, also 4 students here. And topic 16, comprehensive 2-dimensional gas chromatography and its applications, and 4 students here. So here I want to ask group so 11. So if you're in the class, so probably do you want to you can just like reply me so directly to me. So do you want to join any of those group with just 3 students, but then you two have to split? No, you don't want? Okay. So, and then our time will be a little bit tight because now we have 11 groups. Okay, we have 11 groups. So, and then so then that means like say on April 6th, and then so and okay, understand. That's fine, no worry. Okay, so and then so we may lost. So then for each group, please stick to a time. Okay, for each group plus the presentation time and also the QA session time. So total you got 15 minutes. Okay, stick to the time. So because then we without any break, so that will run so until 9:45, no delay. I mean, it's the situation of no delay. So, and please strictly keep to your time since now we have 11 groups. So when the time is up, I will remind you, then you have to stop. Okay. So, and so then that will be the, if you all agree, so that will be the final list. Okay. So now you can stop preparation. So, and then prepare for your oral presentation, group oral presentation, and then follow the guideline. So we post it. So on the view e-learning and prepare your slides, and then so don't be too general. It's better for you to use some case studies, do some real cases, and then to illustrate the application. And then you have to include some of the theory as well, okay? So do not really like to be something like say exactly what we have talked about in class. Then for that one, that part everybody knows already, right? Okay, so try to talk about something like new. Okay, so you're welcome, no problem. So, and then talk about something new, and then so think about it, the application. See, many of them is just about application. So case studies will be good. So illustration, some animation, and picture, and those things to make your presentation more interesting. Okay. So, and yeah, so elaboration, do not write too much words on that. Don't be exactly as the teacher notes. Okay, so because teacher notes, we want to provide information for you to do the revision. So that's why I cannot just write the keywords. Okay, but for your like say, we say research presentation. So this kind of thing, you want to do that with something like more easy to read the slide, not writing everything, not just read your slide. You can just write the keywords and do the elaboration. So for that one, because it's a group presentation, so at that time I will require, so for the students who are doing the presentation, turn on the camera and then show and do the oral presentation. And later I'm going to also upload so the marking sheet on BU e-learning, and then so you will have one representative from each group, so to provide the to input the grade. So actually your group, you will have the chat, right? So you decide together, but you just have one representative to reply me, send the marking sheet back to me. For example, so for those students, so the 4 students, you're in group 1, right? You do the topic, you finish one. You do not mark for yourself. But then, so you give marks to all your peer. Group 2, 3, 6, 7, 9, 10, 11, 12, 15, 16. You provide marks for all of them. But you have 4 students in your group, right? Okay. So, and then only ask one to send back the marking sheet to me. Okay. So that one, the mark in the marking sheet will be the mark that given by all of you. Okay. So it's just like saying one mark for the other each group, okay, and give it to me. And then I will also give mark for each group based on our presentation performance. And Dr. One will also give you the mark. And then we have waiting for that, right? I mentioned that you can, if you forget about it, so just go to check the guideline and you will see that. How about that? And then so we get the final mark, and for each student in the group, you get the same mark. You get the same mark. Okay, so that means all of you have to contribute. You have to contribute to the preparation of PPT slides and the content. You have also contribute to the oral presentation. For example, if we have 3 students, so like say if we have 12 minutes for presentation, that means each of you got about 4 minutes, right? So if you have the 4 students, that means each of you got what? Each of you got, let's say, about 3 minutes. Don't have to exactly the same, but about. Okay, so because each of you have to get involved, and this is group work. You work together, and I highly recommend you guys to do some rehearsal online, so you can create your own Zoom meeting and have your group mates join the Zoom meeting. Like you guys organize a time to do the rehearsal. So before the presentation date, and because you do your own part and put together, and then logically should be sound reasonable, right? So and then your PPT slides should be better to have the same kind of thing, font, format, the background, things like say looks like say is consistently, right? Okay, so and better to do rehearsal before that. Well, you got time to do so, and you can start preparing now. So and we'll do that on April 6th. Okay, so now remember the topic that of your group. Okay, for now, and I'm going to upload this one on BU e-learning after class. Okay, so good for now. If good for now, so we'll go back to the slides. Okay, so we're going to continue talking about, so ion chromatography. Okay, so this one. Okay, good. Okay, so now let's look at this influence of different parameters. So on ion chromatography, now we're just using ion chromatography as example. Ionic strength, definitely ion strength. So ion strength, the concentration of the competing ion, right? Okay. So and also the nature and property of the competing ion. So the eluting ability increase with the eluent ionic strength. So and the selectivity among ions of equal charge is only marginal, but however, the selectivity among ions different charge. So let me say that means the divalent ion shall have much stronger elution power than this monovalent one, right? Okay. So, and how about the pH? Reorientation time of ionized weak acid increase when the pH of eluent increase, right? Okay, because when the pH increase, so it may be more neutral form, right? Okay, so and be like say, oh sorry, the ionized form, sorry, and then so it will be like say higher affinity and retention on that. So it because the sample ion charge being controlled by the pH, the more basic the eluent, the stronger the negative charge, and then so you have higher affinity. So in a suppressed system, so and the eluent pH is much higher so than the pKa of most analyte, right? Because we're using bicarbonate buffer, which pH around 10, and we use the sodium. If we use sodium hydroxide, pH even higher, around 12, right? So, and then, and so pay attention to those things. And then so we mentioned that if you're using the carbonate and bicarbonate system, so and you may not get enough sensitivity for those very weak one like acetate because of the suppressor and the pH of the eluent is around 4, and the pKa value of the acetate actually is about 4.3 something, 4.74, and it's not fully dissociated. And also we also talk about the sodium hydroxide when you get too basic, and then when the phosphate ion may not be the hydrogen phosphate 2-, so it may change to the triplet charged one, the phosphate ion, right? So temperature also play a role. So and exchange rate between the stationary and mobile phase increase. So with increasing temperature, okay. So and then so viscosity and decrease. So with increasing temperature, okay. And however, so we know that we cannot do the run at very high temperature for the stability of the column. And for flow rate, if you have faster flow rate, of course you have smaller retention, so it comes out faster. But also this flow rate relate to the back pressure, the pressure drop, right? Okay, so and relate to that one, and also the buffer salt, talking about elution power of the eluent, so which is the nature of the buffer, the salt. Again, we think about the charge density and then selectivity, that one. So and so on. So this is something like pretty general. I think after we talk about in so much detail just now, and then it should be easy for you to understand now, right? No difficulty, right? Okay. So how about the count time? How about the choice of eluent for count time chromatography? Remember example we just see right now? The example I showed you earlier. So that one used what? MSA, the methyl sulfonic acid. So well, that is, remember in that example, we have the separation of the lithium, sodium, potassium, ammonium, together with calcium, magnesium, right? So we have both the singly charged and the doubly charged, okay, divalent ones. But how about for just like say for those simple one? If for the separation for alkaline metal, ammonium, and small aliphatic amine, so on strong acid cation exchanger, so that is for very simple one. So a singly charged one on strong acid cation exchanger. So mineral acids such as hydrochloric acid, and also sulfuric acid, okay, diluted one, okay, and nitric acid. So they are typically used as diluents. So don't matter whether the conductivity detection is carried out or with or without so chemical separation. So this is the one often used. However, so the concentration, okay, normally between 2 millimole to 40 millimole. However, if you want to do the simultaneous analysis of an alkaline metal, alkaline earth metal, that means if you also want to do that for magnesium and calcium together with that lithium sodium, when we say that, remember we say much larger affinity than like the single valent one, okay, the monovalent one. The divalent one much stronger affinity the monovalent one. So that's why. So this one, if you're using a strong acid, strong cation exchanger, so you have this, the binding will be too strong. If you're using this column, that would be too strong and very difficult to break. So that's why if you want to handle both the monovalent one and divalent one, you have to use the weak cation exchanger. You have to use a carboxylic based one. The example I showed you guys earlier is actually a mixture of carboxylate and phosphate, okay? But anyway, the weak acid cation exchanger. And then for that case, so either the MSA, the methyl sulfonic acid, or sulfuric acid, so they are recommended as diluent. But the key point is if you want to handle so the alkaline earth metal and also the alkaline metal together, do not use a strong cation exchanger. Use a weak cation exchanger. Okay, understand? And then so the concentration rarely exceed 2 millimole per liter. That's a key point. That's a key point. And how about the buffer one? So how about those, the buffer capacity? Since both mobile phase and solute ions, especially say this one example show that, can be affected by pH. So the buffering capacity of the mobile phase is very important. So that's why the phosphate, the carbonate, bicarbonate system is a very good buffer system, okay? So, and ability of the complex of the ion sample compound, this is for when talking about transition metal. So if you want to using an ion chromatography for transition metal, so the complexing agent often added. So it may form complex with those transition metals, so that could change its original charge and degree of ionization. The new species will have different retention times, and so and that separation finally will be maybe affected. Okay, so it could be affected. So organic modifiers, so and sometimes we add water miscible organic solvents such as methanol, ethanol, glycerol, acetonitrile, and so on to add to it. So one way for that is see if found that the methanol containing diluent can significantly increase K value. So if methanol added could increase K, so an increased resolution, then because K and better retention, right? Increased resolution between ions may have similar K value may be better separated. In contrast, so the shorter retention time observed for ACN. So if ACN, so and the K value decrease. So how to say, so this solvents is possible because when the explanation is not really so confirmed, it's just say maybe solvents can affect a variety of parameters related to the separation process, such as alter the affinity of organic ions to the stationary phase, may alter the degree of complexation. So if you're dealing with that, okay, so the complexation of transition metal, or it may change the degree of the ionization of weak acidic and basic ions So either in the mobile phase or stationary phase. You can see this one. Example here, it has sodium hydroxide and acetone nitrile. So it's for separation, actually, it's not really for organic. It's just for normal one. So we have seen that for many times, right? Okay, but you can see here now the number 7 is also phosphate. This one, because now it has so and 0.04. Okay, so it's 40 millimole, that one. So and 95 to 5, very high. So you can see the acetonitrile with increase of the proportion of acetonitrile from 50 to 25 to aceton 2 and 40. So everything squeezed out here. So and 75% is the better one. So my understanding is probably is because acetonitrile, this one. So they make the polymer because the duration now is hydrophobic polymer, right? So and then so I make it like kind of high. The surface like say more hydrophobic than the diffusion of ions to the stationary phase. So decrease, then not really easy retained. But this many could affect a variety of parameters. It's really hard to say. But anyway, so if you use ACN, so and can observe a decrease of the K value, but methadone will be increased. You can see the ACN number. So, and this is also influence of ACN on the retention of alkaline and alkaline earth metal. So this one example is for the ionize, inorganic ionize. It can influence, but it can also influence the cations, right? It also can have influence the cations. So, and then you can see the eluent now is 10 millimole of this MSA acetonitrile, and then so, and you can see it can be even faster. So if you're using 10% of ACN. So anyway, so this is how it comes out. So it shows that one. Okay. So for the detector of the ion chromatography, so because the ions, they are conductive. So the most popular detector is the conductivity detector. Okay. So, but however we say that, because you see now I'm just using the ion chromatography as example. So you're having carbonate, okay, bicarbonate. So those are ions, right? So you're using a certain like millimoles of those ions, carbonate or bicarbonate, as the eluent, as a mobile phase. So they are quite conductive as well. They have high conductivity as well, right? So they also, the background already has the signal. So, and so therefore, so if you want to have enough sensitivity, so you want to convert this two to something less conductive. And then you also want to, for example, here, this is your mobile phase. Here is a mobile phase. You have this buffer, and your analyte, borate, chloride, so nitrate, and sulfate. Okay, how about that? So you want to decrease the signal of your mobile phase, and you want to increase the signal of your analyte. So how can we do that? So because you want to lower the signal from background, and then in overall you have a higher signal to noise ratio. So that is the idea of the suppressor comes out. Okay, so the suppression, so to suppress what? To suppress the signal coming from the mobile phase, the background signal. Okay, so the suppressor is used when conductivity detector, so it's needed when conductivity detectors are used. And the mobile phase, so is intensively conducting, so therefore the suppressor will chemically reduce the background conductivity of the mobile phase. And then, so the reaction aim also to increase the conductivity of the analyte. So because the suppressor is used before detector and it considered as part of the detector. So you can using the packed column with exchange resin or ion permeable membrane tube, or like even nowadays in 1992, the invented the self-regenerator suppressor. Okay, so the simplest form, so it's just a chemical suppressor. So the chemical suppressor looks the same, so it's actually similar to the exchanger. For example, so the suppressor can be can just really release hydronium ion or hydroxy ion. So depending on the mobile phase. Now let's talking about, first we talk about ion chromatography, okay? I9 and I9 IC, how about that? Just I9 IC, okay? So talk about I9. So now for the I9 IC, we know, so we want to reduce bicarbonate and we want to reduce carbonate. At the same time, we want to increase fluoride, we want to use chloride, okay? So then the suppressor now, the simplest form itself is a cation exchange column. What do I mean? The suppressor, the resin is negative charged. And so it's an ion exchange column in hydronium form. That means the resin, the suppressor, here's suppressor, okay? The suppressor itself for this ion exchanger is a cation. Okay, it's a cation exchange column for this online chromatography. So, and then it is in its hydronium form. It has hydronium ion kept on it. So when your mobile phase and analyte pass through the suppressor, what happened is because hydronium ion, do you remember this affinity order? Just want to show you. Hydronium ion here. So hydronium ion, so it can be replaced so by sodium, because sodium has strong affinity, more competing, right? Okay, so sodium, so in the mobile phase, okay? So you can see that. So that's why you can, why hydronium ion can come out, okay? So, and then your mobile phase goes to, and then, so hydronium ion is replaced by sodium. So sodium not in on the resin. Hydronium ion comes out. Hydronium ion comes out. So hydronium ion comes out. So it react with bicarbonate ion, and carbonate ion use carbonic acid, which is the weak acid. Okay, so, and it also comes out here. So, and it forms hydrogen chloride. Okay, so here is actually, they are totally dissociated. Okay, so, and the pKa value, if you still remember that, the pKa value for hydrogen, for carbonic acid is about 6.8. Okay, so, but now, so the overall pH of the eluent comes out is about 4, because many of this hydronium ion now shows up. So that means in this solution pH equal to 4, so the most carbonate and bicarbonate now, they are now in the neutral carbonic acid form. So when that means they're less dissociable now. So then therefore, so their conductivity has greatly dropped. So by doing so, you can see that now we have convert, so the eluent ion, so to less conducting carbonic acid. Well, how about the analyte? The analyte now, the sodium replaced by hydronium ion. Hydronium ion is most conducting, so cation. So, and let me see whether I have that number for that one. Yeah, here I have a number. So, and if we talk about conductivity, so, yeah. So if we talk about the conductivity, So for hydronium ion, so it has number is 350. Okay, so the unit for that one, so here is the unit probably. The unit is so cement square centimeter per equivalent. Okay, so this is a unit for conductivity. So now for hydronium ion, it has so 350. Of course, in the water, so it is hydrated by water. So we have this one. Okay, so and 350 for potassium. So conductivity is 74, and for sodium ion, conductivity is just 50. So now the sodium replaced by hydronium ion. So the conductivity of the analyte now in the acid form so have been greatly increased. But for the background, so the conductivity has been greatly decreased. So that's why. So now the sensitivity has been greatly increased, signal to noise ratio. So, and indeed, by using this suppression, it's possible to detect several common ions. So for the concentration as low as 10 ppb in 25 microliter of injected sample. So understand now, everybody here? No problem, right? No problem. Okay. So how about the kind time? Okay. So a similar. So similar if you want to for kind time for this one. Now we have acid as the eluent at the mobile phase, which is the acid. So it's the eluent. And then we separation for sodium, for potassium, for ammonia, and so on. But you want to release that. So for kind time IC, cationic IC. So now the exchanger is the anion exchanger. It's anion exchanger. It is hydroxy ion form. It's hydroxy ion form because now this is what you want to measure, right? This is what you want to measure. Before the mobile phase is a strong acid. It's really conductive. It's really conductive. Okay. So now, so the chloride, because this hydroxy ion has the least affinity, right? So chloride can easily replace it, and replace it, and then release hydroxy ion out. And hydroxy ion out, so you bind with hydrogen from water. Water is very low conductivity. Okay, so the conductivity of the mobile phase so now greatly decrease. But however, for the sodium chloride, now the conductivity becomes sodium hydroxide. So for your information, again, so this one, let's see. So, and if we talk about conductivity, the hydroxy ion is the one, so with larger conductivity, okay, the unit I'm not going to write again, so it's same as for the previous slide, okay? So the carbonate, so conductivity 72, and then so the bicarbonate, this one conductivity 45, and then so for chloride, conductivity 76. So you can see now you replace chloride by 198 by hydroxy ion. So the conductivity of your analyte greatly increase, and the conductivity of the mobile phase greatly decrease. Then so that increased the signal to noise ratio. Okay, so clear? Understand now? No problem. No problem. It's good. So and then so we're going to move on. So and then so this is a very simple form. Very simple form for what? For this suppressor. Okay. And there are some others operation method for suppressor besides this one. So and can be the exchange of the this one. Yeah, this is what we already talked about. Okay. So and then can also completely remove the eluent ions by precipitation, such as removal of the barium, and lead ion by precipitation of sulfate. This is another method to do that. Or reduce the ion charge in the mobile phase by complexing them with copper, other complex agent. So if it's mobile phase containing the chelate, so that is the option to do so. Okay. And then however, that is the simplest chemical form. So, and in 1992, so people even invented a self-generating suppressor. So, and this is how it looks like. It has two platinum electrodes. So one is the anode, the other is the cathode. So it's on the top and the bottom so of that device. And then so it has two regenerant chamber. Okay, for example, in this is a figure for that. So this is an anode, this is a cathode, this is a regenerant chamber. What happened in this regenerant chamber is electrolysis of the water. You can see water in the anode. So it has been to oxidized to oxygen, okay, and they form the hydronium ion. So water in the cathode has been reduced to hydroxy ion and hydrogen gas. Okay, so and this one, so water, just like say electrolysis, and so in this two chamber, one convert to hydronium ion, the other one reduced to hydroxy ion. But then in the middle is the reaction. So it's your eluent goes through in the middle. So here you can see the eluent and your sample goes through in the middle. But here, so the inside this middle is separated from this two regenerating chamber by two cation exchange membrane. So that means the membranes only can allow cation to pass through. So what happened is like say an anode, because the hydronium ion, this one is formed. So this hydronium ion is positive charge, is attracted by the cathode because negative charge. So it's moving that way. Unfortunately, because now this membrane only allowed cation to pass. So hydronium ion basically can pass through this membrane and get into this eluent chamber. And then cation, so the hydronium ion, so hydrogen ion, so get into the chamber, and then so now it combined with carbonate and bicarbonate eluent to form this much less conductive carbonic acid. And also it can and together with this fluoride, chloride to make them to the acid form. At the same time, sodium, so in this chamber, so it's attracted to the cathode, and then moving this way forward and come to this side, and then so they all go together with some the waste. Okay, so and here you can see in both electrode, some oxygen and some hydrogen formed, but because the hydrogen amount gas here formed is very small amount, it not really have some explosion hazardous, so that concern. So it's still safe. Okay, but you can see here, and then so once get convert to the less conductive carbonic acid, and then so go to the detector, and then so the water basically can recycle and then go on. So this is called self-regenerating suppressor for that. How it works. I can see this after suppressing, the signal for the mobile phase now is very low, and then so the mobile phase, when you have a sample, you can see so enough sensitivity to see the sample to pass through. Okay, so and for detector, the conductivity detector is the universal detection. So all the ions, they're electrically conducting. So and it's simple to construct and to operate. And the conductance of solution is determined by its ion strength, type of species solution, and temperature. And as we mentioned, I will show you the number. The most conducting ion is hydroxy ion. So the most conducting cation is hydronium ion, right? Okay, so that's why. So, and they replace that into to increase the signal of the analyte, and then they convert so the signal of the mobile phase to less conductive species. So the conductance of ion increase with its charge density and decrease with its viscosity. So if the analyte is fully ionized, the conductance so is proportional to its concentration. So this is how we do quantification. Okay, so that means want to be fully ionized. Okay, and then so it conductance proportion to its concentration. The detector responds to analyte concentration, so and the degree of ionization of eluent and also the analyte ions. So and so that means you want it to be fully ionized. So that comes to the issue of the weak acid. So and we have to do the eluent suppressed. So here you can see that. So because remember I say that after the sodium carbonate bicarbonate system, they go through the column and then suppressor, the pH of the eluent under is about 4. It's about 4 because it has the carbonic acid, it has also the hydronium ions. Okay, so and then however, so for acetic acid, so its pKa value is 4.74. What does that mean? So that means for this one is 3.18. Okay, that means that's it for especially for acetic acid. Now it's under an even more acidic condition, so it's not fully oxy. It's not fully dissociated. It's not fully dissociated. So and it's just partially dissociated. So when they are diluted, okay. For example, if you can see now pH equal to pH 4. Now pH equal to 4, right? How about we do this one here? pKa 4.7 plus log acetic acid AC minus acid form. Okay, so we can calculate if you try it yourself. So that'd be like here will be minus 0.7. So this result in its acid form to its dissociated form to its neutral form. This one only equal to 0.18. That means only about 20% or only about 18% dissociated. So it's not fully dissociated. So the sensitivity is not enough, just partially dissociated. Okay. So and also, however, when the concentration increase of acid increase, and then of course the solution will be more acidic. So right, the pH will further decrease, and then that will make what? If this will further decrease and make more negative, right? And then so that means even more difficult for the acid to dissociate, and then the dissociation may go to like even less than 0.18, right? Okay, and then so that's why. So and it's not a linear relation. So when the acid concentration so increase, if it's conductivity, and then so it will be a curve like this one. It's not straight, so it's even lower. It's non-linear. Okay, so a fraction, because the fraction of acetate ions further decrease with increasing concentration because the solution becomes even more acidic. Okay, so even harder for it to dissociate. So besides the conductivity detector, can we use other detector? The answer is yes. So and can use the molecular, so UV visible spectrometer, and then so but for this one, so most of the ions actually they do not have UV visible chromophore. So that means like say if you're using UV visible absorbance, you may want to do that indirectly. What does that mean indirectly? That means in the mobile phase, your mobile phase may have high response. Your mobile phase may those like salicylic acid, something like that. The salate, okay? So which is like saying because salicylic acid has aromatic ring, COH and COH, right? Okay, or benzoic. So this one, so COH. So it can be the salad, then you'll be like say the salt here, right? Okay. Or like benzoate. Okay, so if you can be that kind of the mobile phase. Okay, then they will have, because aromatic ring here, so they have a strong UV visible absorption. Now you have, say, you have your chloride, so you have those things like say your ions, so they're not really like say UV visible absorption. So then they will cause a dent like this one. So there'll be your inorganic ions. They will not UV visible absorption. So this is the UV visible absorbance. So you'll be like say have negative peak. So here, and then so after round, so you just switch the polarity of the detector, and then it will be something like this. Okay, so this is how you do when you're using the UV visible absorbance. So because your analyte is not really UV visible absorption sensitive, so you can using a high UV visible absorbing reagent, so like the mobile phase, like salad benzoate. And fluorescence can same, you can do the indirect one. So using mobile phase, which has strong fluorescence, and then the analyte don't have, and then they have the dent negative peak, and then you do change the polarity. Okay, so refractive index seldom used, and then so, and you can also like say the other detector, so ion. So we can use ion chromatography connected to ICP-MS. So that's a good technique, because for that one, so you can not only use ion chromatography to separate the different oxidation state of the same element. For example, you can separate so and ferric ion and ferrous ion, iron 2+, iron 3+, right? And then so you can use the ICP-MS to even quantify the isotope so of the metal, right? So this is pretty good. Okay, so that's a detection technique. So let me see, we're running out of time, right? Okay, so how about we stop here? So we stop at page 55, and then so and we let me know so if you want any help. Okay, so that'll be all for today. So we stop here. So if you have any question, so you can always send email. So if not sure about any question about oral presentation, also can ask me. But so and I'll see you guys next week. And next week I'll talk about so size solution chromatography, and we definitely can finish that one. So I may even talk about a little bit about capillary electrophoresis. Okay, so and that's all for today. So yeah. Page 30. Okay, for those students, if you don't have question, you can leave. For students, if you have questions, so now we'll answer question. Page 30. You mean this one? Between adjoining more pronounced than so and doubly charged ions. So and this one maybe not really expressed in the right way. Okay, so what I want to say, yeah, I need to rephrase that. So what I want to say is like say the concentration influence. So like say this one, you see that when we increase ionic strengths, so when the ionic strengths increase, so the influence on this divalent ion seems to be more severe so than this so monovalent ions, right? Do you see that? So when we increase the ionic strength, then say that we increase the K value of the sulfate and the hydrogen phosphate decrease, let's say, more severe than that, the influence on those single valent ones. Okay, so I'm saying like say, then for those single valent ones, so their behavior is similar, and for those divalent ones, then the behavior is similar. So I actually want to say in that way, probably I expressed in maybe the confusing way. Okay, so this is what I want to say actually. Probably I revised that one. Okay, did I answer your question? Yeah. Okay, good. So, and any other question, guys? If you have other question, you can also ask. So, yeah, because of a lot of content today. So about the ion chromatography, because we talk about very details. So if no questions, fine. So if no question, that's the end of today. So, and goodbye. So bye, guys. Yeah.